Kepler gave three laws of planetary motion. First law deals with the orbits. So first law is also called as law of orbits. Second law deals with the areas swept. So second law is called as the law of areas. And third law deals with the time period of revolution of the planet around the sun. And that third law is called as law of time period. Let us first discuss first law of planetary motion, or Kepler's first law, or law of orbit. Kepler's first law, or law of orbits, states that every planet revolves around the sun in an orbit that is not round, that is elliptical, and the sun is situated at one of the foci. Either the sun is situated here, or either sun is situated at here. Now when the planet is closest to the sun, it is called as perihelion, and when it is farthest from the sun, that is called as aphelion. The Kepler's second law, also called as law of areas, it defines that the areal velocity of the planet is constant. That means the area swept by the planet, whether it is far away from the sun or closer to the sun, in the same time is same. That means if a planet goes from position P1 to P2 and at a later time it goes from P3 to P4, if the time is same, the area swept by the planet are the same. That means the area of P1, P2, S is equal to area of P3, P4 into S. Now we see that SP1 is greater than SP3. That means P3, P4 is greater than P1, P2 in order to keep the areas constant. If we divide this by T, that means P3, P4 divided by T is greater than P1, P2 divided by T. Now, P3, P4 divided by T is the linear velocity from P3 to P4, and P1, P2 divided by T is the linear velocity from P1 to P2. That means linear velocity P3, P4 is greater than linear velocity P1 and P2. That means in order the areas swept are same in the same time, the linear velocities of the planet need to be different. That means when the planet is far from the sun, its linear velocity is less. When it is closer to the sun, its linear velocity is more, so that it sweeps the same area in the same time. That can also be predicted from here. The gravitational force here should be less as the distance is more, so the kinetic energy should be less, so velocity should be less. Here, as the distance from the sun is less, the gravitational force is more, so the kinetic energy of the planet here is more, therefore the velocity is more. This is the law of areas. Discussing about the third law of Kepler's laws of planetary motion, it is also called as law of time periods. From the Kepler's first law, a planet moves around the sun in an elliptical orbit. That means we have got two axes. One is the longer one, that is called as major axis. One is the shorter one, that is called as minor axis. The Kepler's third law, or law of time period, states that the square of the time period is directly proportional to cube of the semi-major axis. So T square is directly proportional to R cube. How are we going to derive this equation? Now, when a planet moves around the sun, the gravitational force gives the necessary centripetal force to the planet to move in an orbit. That means if we take Gmm by r square be the gravitational force of attraction between the sun and the planet, that is Gmm by r square is equal to centripetal force, that is mv square divided by r. Here v is equal to r omega, where omega is the angular velocity, v is the linear velocity. So Gmm divided by r square is equal to m r square omega square divided by r. Here 1 r and square goes. We also know that omega is equal to 2 pi divided by t. So putting the value of omega in this equation, we have gm m divided by r square is equal to m r 4 pi square divided by t square. Here m and m goes. Taking t square here and r square here, we have t square is equal to 4 pi square r cube divided by gm. As this is a constant, from this equation we can tell that t square is directly proportional to r cube, which is Kepler's law of time period, or Kepler's third law. This completes our gravitation.